All right, Peter. So today we are going to be doing A levels chemistry, AS, organic chemistry. All right, these are some questions which are handpicked from the organic chemistry section of A levels. All right, so let's start doing them. The first question is describe structural isomerism. All right, describe structural isomerism. So definition is very simple. What is structural isomerism? It is compounds having same molecular formula but different structural formula. All right, these are compounds having same molecular formula but different structural formula. All right, so their structural formula, or you can say they're different structures. All right, different structures. That is also true. Okay, next question. A and B are structural isomers with molecular formula C5H10O. All right, so A and B, they are isomers of each other. They both have the molecular formula C5H10O. Let's have a look. They are both straight chained molecules with only one functional group. All right, they both have one functional group. Okay, sure. Table 5.1 describes observation when separate samples of A and B are added to different reagents. All right. So first, they are added to the 2,4-dinitrophenyl hydrazine, the DNPH reagent. This is the 2,4-DNPH test, and this test is always done to check for the presence of a carbonyl carbon. This is always done to check for the presence of a carbonyl carbon. What is a carbonyl carbon? A carbonyl carbon is a carbon which contains the carbon double bond oxygen functional group, right? This thing is the carbonyl carbon. Now, it could have many things on both sides. It could have hydrogens on both sides. All right, that would be an aldehyde. If it has a carbon chain on one side, let's call that carbon chain R. This is still an aldehyde. And if it has carbon chains on both sides, then it is called a ketone. If it has an OH on one side, then it is called a carboxylic acid. If it has an OR on one side, it is called an ester. All right, so the carbonyl carbon leads to many different functional groups. All right, out of those many functional groups, there are two true carbonyl compounds, which are the aldehydes, which look like this, and which are the ketones, which look like this. All right, the 2,4-dinitrophenyl test, the 2,4-DNPH test, is only positive for true carbonyl compounds, which are aldehydes and ketones. Aldehydes and ketones are the only true carbonyl compounds. Okay, so if A has a positive result for 2,4-DNPH test, that means it contains a carbonyl compound. If B also has a positive 2,4-DNPH test, then it must also have a carbonyl compound. Now, because orange precipitate appears in both A and B, this shows a positive test result for both of them. This shows a positive test result for both the compounds, and because both of them show positive result for 2,4-DNPH test, that means both of them are carbonyl compounds. All right, so name the functional group present in both A and B. The carbonyl functional group. Which functional group is present? The carbonyl functional group. This is the functional group that is present in both of them. Okay, why can't we be sure whether it is aldehyde or ketone? Because the 2,4-DNPH test is positive for both aldehyde and ketone. We can't say aldehyde or we can't say ketone. Okay, we have to use the word carbonyl. We have to use the word carbonyl. Okay, on to the next question. Draw the structures of A and B in the boxes. We have to draw the structures of A and B in the boxes. So one of them must be an aldehyde and the other one must be a ketone. Okay, so because we have to further look at this, why did I say one of them has to be an aldehyde? Because look, A goes on to do a second test, and the second test is the tolerance test. The tolerance test, if a silver mirror appears in the tolerance test, that means that compound is an aldehyde. Compound is an aldehyde. And if no tolerance test takes place, but the 2,4-DNPH was a positive one, then the carbonyl compound is ketone. Okay? So A, because it gave a positive test for the first one, and then it gave a positive result for the second one, therefore it is a aldehyde. A is an aldehyde. So we have to draw A as an aldehyde. The functional group of aldehyde is C double bond O H, right? This is one side of the aldehyde, and now we have to draw the other thing, which is uh, how many carbons? 5 carbons, right? C5. Okay, so one of them is right here, and then we can just go ahead and draw CH2, 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 and CH3. All right, so this would be our aldehyde of C5H10, C5H10O. All right, it's called pentanal. It's called pentanal. All right, and then B, because B is a carbonyl compound because it gave positive test for the DNPH, but it is not showing any positive reaction for the Tollens reagent. Because it is not showing any positive reagent for the Tollens reaction, therefore it means it does not have the aldehyde functional group but the ketone. Then there is a third reaction for us. The third reaction is useful over here. It could have been useful over here as well, but there wasn't much need because aldehydes are only fixed. They have to be made in the corner. But now the ketone could have been formed like this. Now look at this carbon, carbon double bond oxygen, and then I'm going to draw shortly C3H7, right? This could be the aldehyde, or let's not draw it shortly. You might get confused. CH2, CH2, and CH3. Ketone of 5 carbon could also have been CH3, CH2C, double bond O, CH2, CH3. So which one of them is correct? Because alkaline I2 means alkaline iodine reaction. This is called the triiodomethane reaction, right? Triiodomethane reaction. If it is positive for B, meaning for a ketone, then it means the ketone must have a carbonyl carbon which is joined to a methyl group. All right. So in the above case, in this case, the carbonyl carbon is joined to a methyl group, right? So this, if the compound was this, if the formula of our ketone or the structure of our ketone was this CH3 C double bond CH2 CH2 CH3, then the result would have been that a yellow precipitate form, a yellow precipitate form. But since there is no reaction, meaning the carbonyl carbon is not joined to a methyl group. This is not possible, right? So what is the next thing that is possible? The C double bond O. Now some of you might be wondering, why couldn't it be that the ketone, the carbonyl compound, was on the fourth one? Because if we put it the double bond O on the fourth one, then it just makes it look like the second one, because the second one also has the carbon double bond oxygen in the same position as if we put this carbon double bond oxygen on this position, because we start counting from side closer to the carbonyl carbon. So in that one, we would have counted over here. So we only had two options. One was placing the carbonyl carbon in the second carbon, and one was placing the carbonyl carbon in the third carbon. The placing the carbonyl carbon in the second carbon was wrong because of the presence of a methyl group, which would have given a yellow precipitate in alkaline iodine. So therefore, this structure is wrong. So the first structure that it drew should be wrong. Okay. And then this is the only structure which is correct. This is the only structure which is correct, right? So you had to think about that. This was something that was concealed in the question. All right. So writing that way, we have the molecular formula C5H10O. All right. And the compound should be called penta pentane 3 1, penta 3 1. Okay, so this is how you write the compound thing. Okay, this was not necessary. I'm only writing it so that you guys know how to name substances. Okay, so I hope you guys are understanding. Okay, so next we have, oh sorry, I think the screen stopped. 1 second. Okay, we're back. Okay, on to the next question. C is a structural isomer of A and B. All right. C is straight chained and has two functional groups. All right. C shows only one type of stereoisomerism. All right, so C must contain only one kind of stereoisomerism. Let's see which one. Table 5.2 describes observations when separate samples of C are added to different reagents. When they are added to different reagents, here's the table that is showing some situations. Okay, um, and then we have 2,4-dinitrophenyl hydrazine, which gives no reaction. That means there is no carbonyl compound over here. This thing is absent. Absolutely. Okay. Br2 is giving orange to colorless. This is a positive test for carbon double bond carbon, right? Positive test for carbon double bond carbon, right? So you guys, if you guys want to write stuff like this, you can also write it on your worksheets. Okay. So this is a positive test for carbon double bond carbon, meaning our compound C must contain a carbon double bond carbon. And then we have the alkaline I2. The alkaline I2 shows a yellow precipitate appearing. The alkaline I2 shows a yellow precipitate appearing. And then they're saying to draw the structure of C in the box. So we had to draw the structure of C in the box. Okay. So what would be the structure of C? The structure of C over here should contain one thing at least, and that one important thing is that it contains the carbon-carbon double bond. That has been proven from over here. All right, so let's just draw the carbon-carbon double bond at first. Okay, so this must be the carbon-carbon double bond.
सर आपकी स्क्रीन नहीं दिख रही.
Is that true for everyone? बेटा बाकियों को दिख रही है या किसी को भी नहीं दिख रही?
No sir, it's not visible.
You guys can't see or you guys can see?
No sir.
Okay, okay, okay. Can you guys see the screen now?
Yes.
Okay. So the carbon double bond carbon must be present. That has been confirmed. Okay. Now the next thing that makes sense is to think about the molecular formula. The molecular formula of C should also be C5H10O, because as we said, C is also a structural isomer of A and B, right? C5H10O. Now, because it contains one oxygen, what could it be? So, how many functional groups have we studied that contain one oxygen? So, we've studied the alcohol functional group OH, right? That has the one functional group. We've seen the carbon double bond oxygen H and R, that is the aldehyde, which has the one oxygen, right? And then we also have seen the carbon double bond oxygen and R on both sides that contains one carbon as well. This is the functional group, right? Is there any other functional group that we have studied which contains a single oxygen? The answer is absolutely no, right? We have not studied any other. So that means if it can't be aldehyde and it can't be ketone, and why am I sure that it can't be aldehyde and it can't be ketone? Because it gave a negative test for the 2,4-DNPH, which proves that there is no aldehyde and no ketone present, right? So this compound must have the alcohol function. Once that is sorted out, let's now understand the next thing. The next thing is that it must contain alkaline I2. It must contain what? It must contain the alkaline I2. The alkaline I2 meaning that it must contain a yellow precipitate, right? So what does that mean? When we have the alkaline I2 reacting with a compound and a yellow precipitate is preparing, I have explained that there should be a methyl group. There should be a methyl group. So the alcohol should be connected to the second carbon at least. It should be connected to the second carbon at least, right? So it should be connected to the second carbon, and then we should have either we could see and we could have a double bond over here, right? And then we could make the formula C, and let's call it H, and let's call it CH3. Okay, either this could be our uh, thing, the structure, or our structure could be C single bond C, and then this could be CH2, or it could be only CH, because now we have to go to CH2, and then how many carbons do we still have left? Two more carbons. So we could have C, H, and double bond CH2. This could be our other compound as well, right? This could be the other compound that we would have, because we need to have five carbons at least, right? So this is also five carbons like this. Okay. So the double bond could be over here. The double bond could have been over here. The double bond could have been over here. The double bond cannot be over here. The double bond cannot be over here. Why? Because we need to keep this a methyl. We need to keep this CH3, right? Okay. So the double bond could have been over here. Right now there is also one hydrogen with this guy. Okay. So if the double bond was over here, then we have to also look at other conditions. Only one type of stereoisomerism is shown. So yeah. So C shows only one type of stereoisomerism. How can we know that? So if the double bond is right here, then because of the presence of double bond, there could be no stereoisomerism. You guys should know that stereoisomerism is only because of two reasons. One reason of having a stereoisomerism is because of presence of chiral carbon. Like in the structure right now that I have drawn, okay, I don't know if it is correct, but I have drawn it so that this carbon looks like a chiral carbon. Why do I say that this carbon looks like a chiral carbon? Because this carbon satisfies the definition of a chiral center. A chiral center is a center which contains a carbon that is joined to four different species, right? That is joined to four different species. If you join this whole thing, this looks like C3H5, okay? C3H5. So this is C3H5, this is OS, this is CH3, and this is H. Four different substances joined. Therefore, this is a chiral center. This is a chiral center. This is a chiral carbon. So this carbon would show stereoisomerism. That means this double bond should now not show stereoisomerism, because we are saying that C shows only one type of stereoisomerism. C को हमने सिर्फ एक type of stereoisomerism show करानी है, ऐसा structure बनाना है that it only shows one stereoisomerism. So this structure right now satisfies all our needs now. Okay, it satisfies all our demands. So we can take this that it is a structural isomer of A and B, right? Because it contains the formula C5H10O. Okay, it is straight chained and has two functional groups. It is straight chained, it has no branches. All the carbons in a single line, right? All the carbons are in a single line. Okay, and then it only has one type of stereoisomerism, and its stereoisomerism is of only one type. All right, and that one type of stereoisomerism is the optical isomerism. This kind of isomerism is called what? This kind of isomerism is called optical isomerism. If the isomerism, stereoisomerism, was because of the carbon-carbon double bond, that stereoisomerism would have been called geometrical isomerism. Okay. Name the type of stereoisomerism shown by molecules of C. So molecule of C, what kind of stereoisomerism is the guy showing? The guy is showing optical isomerism, because this kind of isomerism is called optical isomerism. Next question. D reacts in presence of sulfuric acid catalyst to form E and water. All right, so D, a compound which reacts in presence of sulfuric acid and it produces water. The structure of E is shown in figure 5.1. So D, whatever it was, reacted to form E, and E looks like this. All right, so if you look closely, E contains an ester bond, right? The carbon double bond oxygen and then a single bond oxygen. So here's a ester bond, right? This is an ester bond. All right. Name the functional group present in E. Okay, so it is ester. Identify the type of reaction that occurs when D reacts to form E. So whenever ester is formed, the type of reaction is called condensation reaction. If you did not know, you could have known it from the statement that was given up above, condensation reaction. How do we know this is condensation reaction? Because in the above statement, we've said that it produces E and water. Because a small molecule such as water has been liberated during the reaction, the type of reaction is called condensation reaction. Draw the structure of D in the box. So we want to draw D in the box. We do not really know D, we only know E, but we can draw D by looking at E. How could we draw D by looking at E? Basically, ester is formed from a carboxylic acid and an alcohol. That is our generic understanding, right? Ester is formed from a carboxylic acid and an alcohol. That has always been our catch. Now, because how our minds are made, naturally we think that carboxylic acid should be a different molecule, alcohol should be a different molecule. But if ever you see that the ester is formed within a ring system, if the ester is formed within a ring system, meaning the ester formation has closed a carbon chain, the carbon chain has closed, that means that this compound itself had a carboxylic acid functional group and it had an alcohol functional group. It had both the carboxylic acid functional group and the alcohol functional group. Okay, so because of the presence of the ester bond like this, and because the ring system is now closed, we can confirm ourselves, हम लोगों को इस बात का इत्मीनान होना चाहिए that the alcohol functional group and the carboxylic acid functional group were on the same carbon chain. They were in the same molecule. The same molecule reacted by itself. It's like how we used to play snake and ladder, and the snake eats its own tail, right? Like it's going to join with its own back, like that. Okay, so we are going to try and produce the carboxylic group and the alcohol group out of it. How do we do that? We break this bond, right? First of all, this bond needs to go, right? We break this bond. Once we break this bond, this chain will become straight. If you want to see how this chain will become straight, the answer is very easy. Look, so at the end you will have oxygen. All right, then you have the straight bond like this. This bond has been made, and then there is a branch on this bond like this, and then there's this bond like this. Okay, so we have made the branch and we have made this, and then we want to make another bond like this. Okay, then so we have drawn this bond, and then we make another bond like this. So we have drawn this bond, and now we are left with the carbon carbon double bond. So we are going to draw the carbon carbon double bond like this. Like this, and now this is the structure that has formed from breaking this compound, right? But where is the alcohol? Where is the carboxylic acid? The alcohol and carboxylic acid are hidden right now because of the water molecule that also formed, right? If we show that the water molecule, the H and OH also have to be shown. So the OH always goes and joins with the carboxylic group, and the H joins with the alcohol, because that is how condensation had taken place, right? So this is the structure we have to draw, but because we have to draw the structure, so we are going to draw the structure like this: HO, the alcohol group, right? And then we are going to see how many carbons are there. Carbon, 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 4 carbons, right? So we are going to say HOC, and then it also has a CH3 up top, right? So we are going to write, and because it has made 3 bonds, so it has 1 hydrogen, CH, CH3 bracket, and then we have CH2, and we have another CH2, because there have to be 4 carbons in a row, 1, 2, so we draw this, okay, we've drawn this should have CH2 as well, and now we have the last one, which should have COO. Okay, so this is our compound that must have formed. Okay, so this is the compound that must have formed. If you want to draw it with the bonds, it should look like this: HOCH. Sorry, you should not draw H with the bond. You should only draw carbons: CH3, CH2, CH2, COO. This is how you draw the structure. And then if you want to name it as well, because naming compounds is also important. How would you name this compound? The molecular formula of this compound would be The molecular formula of this compound will be 1, 2, 3, 4, 5, 5 carbons, C5, hydrogens how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10, O3, C5H10O3, and the compound's name is, how do you name it? The numbering starts from over here, 1, 2, 3, 4. All right, so you're going to say 4 methyl, 4 hydroxy, butanoic acid, because there are 4 carbons, butanoic. So this is how you name it, because it contains 2 functional groups. You are going to have to prioritize one of them. If there is carboxylic acid, then all the other functional group, whichever functional group is over there, you are going to ignore it. You are going to ignore it as the main functional group. You are not going to choose this because of the presence of carboxylic acid. So the compound is a butanoic acid, and then the alcohol is just added to it. So alcohol is just added to it as a hydroxy. This is how you name this compound. Okay, so you could have done any of the 2 structures and your answer would have been considered correct. On to the next question, beta. Compound C and D are alkenes with the same molecular formula C5H10. C and D, okay. Give the systemic name of D. We want to give the name of D, all right. So D will be named like this: first carbon, second carbon, third carbon, and fourth carbon. On the third carbon, there is a methyl branch. We always write the branch first, 3-methyl, and then 4 carbon straight chain. So we are going to say bute, because 4 carbon is bute, and because it contains a double bond on the first carbon, so we are going to say bute 1 ene. It's going to be called bute 1 ene. All right, 3-methyl bute 1 ene. Next question: explain why C and D do not show geometrical cis-trans isomerism. But neither C nor D shows geometrical cis-trans isomerism. Why? Because to show cis-trans isomerism, the carbon that is unsaturated must be joined to 2 different types of species. Otherwise, cis-trans isomerism or geometrical isomerism is not possible, right? Because how would you consider cis and how would you consider trans? Because right now, how would you consider that this molecule right now is a cis molecule or a trans molecule? How would you know it? There is no way, because it is not possible. According to chemistry, this is not going to form geometrical isomers, because both the bonds or the compounds that are joined to the unsaturated carbon, they are same, both the species, they are both CH3s, right? And then in this situation, what's the problem? Why can't this be? Because if you look at the carbon carbon double bond, this carbon right here is joined to 2 hydrogens. Once again, the same kind of problem, is joined to 2 of the same species, right? So whenever you have 2 of the same species, you cannot show geometrical isomerism. This is a very important fact. Okay. So we are going to say, or we can just let it stay over there as well. So the answer, to answer this question, we have to answer it very simply. So how would you say? Because they are asking for C and D both. So we are going to say both C and D, both C and D contain same type of atoms joined to one of the unsaturated form. Full stop. All right, this is how you have to answer. Draw the structure of a molecule that is a positional isomer of C and D. So we want to draw another molecule of C and D, but it should be a positional isomer. Positional isomer means any substance which has functional group at a different position, any structure which has functional group at a different position. So how could you have functional group at a different position in butene? You honestly could not, right? I mean, the position that would be different for this is going to be of the methyl, because look, if the carbon double bond carbon is joined over here, then it is going to be one type of isomer. If it is joined over here, then it is second type of isomer. But if the carbon double bond oxygen, the carbon double bond carbon, if it is joined over here, right, then numbering starts from this side. So the double bond is always either on the first carbon or it is either on the second carbon, like in the first option right here, right? So what could be different? Now the difference, the position that could change would be of this methyl branch, because in this case it is on the third carbon, it could be transferred to the second carbon. Okay, so that is all we have to do. All right, so we are going to do it like this: CH2 double bond C, and the methyl branch on the second carbon, CH3. Okay, and then because one bond, oh no, we don't have to draw hydrogen with it. Okay, because this is the fourth bond and we have to draw four in a row, right? So just CH2 and CH3. Those who do not want to write it with the bonds, they can write it like this: CH2 C bracket CH3 CH2 CH3. This is how you can also write it. It is difficult to understand for a normal person that it contains a carbon-carbon double bond, but the examiner's checking would know that you have drawn it correctly. Okay. Next question: give the structure formula of the compound formed when D reacts with H2 in the presence of PT catalyst. All right. So we are doing the next question. So D, which is this guy, is reacting with H2, which is hydrogen. So this is electrophilic addition reaction in the presence of platinum catalyst. This is hydrogenation, and hydrogenation of an alkene, meaning a compound containing the carbon-carbon double bond, always produces an alkane. So all we have to do is just remove this double bond and one hydrogen with this guy, one hydrogen with this guy. That is also not even visible. We have to draw the structure formula. So we are going to draw the structure formula like this: CH3 C H, because now in D this carbon is only having three bonds, so one bond is hydrogen, right? So CH and then bracket CH3 bracket close, and then over here would now be CH2, and now over here would be CH3. So we are going to write CH2 CH3, right? C2 CH3, all right? So this is how you can draw. Okay, on to the next question. C can form an addition polymer. Draw the structure of one repeat unit of this addition polymer. So we want to draw the structure of one repeat unit of this addition polymer. So for that, first of all, we have to show that this polymer looks like this. All right. This side contains both CH3s. How do I know that? Because look, this side contains both CH3s. CH3 over here and CH3 over here. Okay. What else do we have? We have another CH3 on the second saturated carbon. So on the second saturated carbon, we have yet another CH3, and then we have just one hydrogen. So how do we polymerize it? How do we polymerize it and show one repeat unit, right? All we have to do is just carbon, CH3, CH3. This is how you draw addition polymers repeat unit. So you had to draw just this. Okay, this is not what you had to draw. I've just explained how you draw it though. Okay, so beta, this is how you draw a repeat unit, and when you draw a repeat unit and when you end it, make sure to make brackets because you want to inform the person that this is a repeat unit. All right, this is a single repeat unit, and thousands of molecules like this are joined with one another to form a single polymer. To form a single polymer, thousands of molecules are joined with one another. All right, I hope that makes sense. Now, let's move on to the next question. C and D both react with HBr. C reacts with HBr to form E. Okay, so they can react with HBr. This is also an example of electrophilic addition reaction. Why? Because C and D are both unsaturated carbons. They both contain carbon-carbon double bond, if you remember from above. Complete the diagram in figure 4.2 to show the mechanism for this reaction. Draw structures of organic intermediates, include charges, dipoles, lone pairs, electrons, and curly arrows as appropriate. So what to draw curly arrows? So because this is an electrophilic addition reaction, our focus is on the electrophile. The electrophile is the hydrogen, which has partial positive charge, and bromide, which has partial negative charge. What will happen is the electron rich density will be attacked by this partial positive hydrogen. Even though I say hydrogen will attack the electron dense region, we still see that the electron dense region has an arrow towards the hydrogen. That is because the flow of electron is always shown from electron rich species to electron deficient species, and every arrow represents flow of electron, right? So what happens to this bond then? This bond is just completely consumed by this bromine, which was partially negative. Now it will become partial positive. Okay. Okay. Now the next thing is we have to see that bromine is joined to this carbon. So carbocation should also be this carbon. So let's draw this like this, right? And then this is the carbocation. This is the carbocation. We can draw it right here and show that this is the carbocation. Now, because the bromide is going to be negatively charged, it's going to be attacked. It's going to attack the carbocation, and it's going to form halogenoalkane. It's going to form halogenoalkane. All right. When you draw the bromide ion, after it has snatched a pair of electrons, that pair of electrons should also be expressed in the diagram. All right. This is how you draw this mechanism pathway. All right. This is the reaction mechanism pathway. You had to draw this. It was very important. Next question. D reacts with HBr to produce F, a chiral bromoalkane. Draw the structure of F. So first of all, we have to remember the structure of D. D was this, right? And where is the carbon-carbon double bond on D? On the final carbon. All right. And what what is produced by HBr is F, which contains a chiral center, meaning once we react it with HBr, all right, the H could join with this and the Br could join with this, or what we could see is the H is joined to this carbon and the Br is joined to this carbon. All right. Now, how would you know which is going to happen more likely, which is going to be more likely to happen? Because according to Markovnikov's rule, the carbocation that is formed that is going to later be attached to this bromide has to be more stable, and the stability depends upon number of carbons it is joined to. If the carbocation is primary, meaning it is joined to it is a positive, the carbocation is primary, meaning it is joined to only one carbon and it is joined to two hydrogens, right? This is a primary carbocation. A prime example of a primary carbocation is a carbocation at the corner. The corner one, whenever that carbocation forms, that carbocation is always primary because it is only joined to one carbon. That is why it is the corner carbon, right? Okay, and then the inner you come, the more stable the carbocation gets. Like this carbocation is stable, and then this carbocation is most stable because it contains three uh, bonds. Okay, so this is why it is a tertiary carbocation. Okay, so if this carbocation had to be formed, this would have been the tertiary carbocation. Anyways, with that being understood, so this carbocation is more stable. Therefore, the HBr should be placed over here. Okay, so the Br should be placed over here. And when the Br is placed over here, let's look. CH3, C, CH3, CH, carbon, 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 and now we have the chiral one. C, no, I believe this one does not contain the branch like this. It contains Br, right? This is this carbon. So we are pursuing that it contains the Br, okay? And then it has one hydrogen, then a CH3. Okay. So if you look at this diagram, you can clearly see that it contains one chiral carbon, right? Contains one chiral carbon right here, chiral carbon. All right. I hope that makes sense. On to the next question. Explain why the reaction of HBr with C and D produces different major products. Why does it produce different major products? Because very simple, the presence of carbocation. All right. In this one, once the double bond breaks, this carbocation is tertiary. And in this one, once the double bond breaks, this carbocation is secondary. All right. So the most D can do is pull a secondary carbocation which is stable. But what C can do is pull a third tertiary carbocation which is even more stable. And the more stable a carbocation is, the more its chance of producing. All right. So the more are its chances of production. Okay. So this um, how do we answer this question? We are going to say which kind of carbocations they form. All right, the question is of 2 marks, so we have to just explain that C forms a tertiary carbocation, whereas D forms a primary carbocation. All right, C forms a C forms a tertiary carbocation at its second position, which is more stable, and it produces, because this is the tertiary carbocation, bromine would join to that one. So we are going to say 2-bromo because bromine is going to be joined on the second carbon. 2-methyl. There's also a methyl group. And then 4 carbons in a line, butane. Methyl. So you stop. Next, on the other hand, D is a D forms a secondary carbocation. D forms D forms a secondary carbocation and hence so if the secondary carbocation is this, then we would say 2 bromo 2 bromo 2 methyl butane. All right, so D forms 2 bromo 2 methyl butane. I hope that makes sense. On to the next question. C can be used to form H. So this is H. Okay. One possible synthesis of H is shown in figure 4.5. Different proportions of C are used in reactions 1 and 3. Some of the products are then combined to produce H. Figure 4.5 does not show any of the inorganic products of the reactions C, and then there's reaction 1, and then E, and then there is J, and then C, there's reaction 3, it is G and a ketone, as you can see, and then there is J and G reacting to produce H. All right, and H looks like that over sure. So now complete table 4.1 with reagents and conditions required for each reaction shown in figure 4.5. All right, so the first reaction is reaction 1C to forming E, that is reacting with HBr. C forming E is HBr. It is an electrophilic addition reaction. Okay, sure. And then E producing J, E producing J reaction to what reagent should be used. Now that is just idiotic because for the first look that you're going to take, you're going to see this and you're going to be like, what the heck? How am I supposed to do such a question? I mean, look at this question. E is going to make J, but I don't know J, so how do I know which reaction I want to use, which reagents I want to use, right? So that is wrong to assume, but we can judge what J is by looking at this reaction, right? We can judge what J is. So what is J? So to identify J, we can eliminate G out of H. So what would be G? If you look at this, out of an alkene, if you want to make a ketone, the ketone is made by hot concentrated acidified KMnO4, right? What do you do is you look at the carbon-carbon double bond, right? You look at the carbonyl carbons. Sorry, you look at the carbon-carbon double bond, the unsaturated carbons, and you say, "K, her unsaturated carbon टूटता है and it produces two compounds. If one of the carbons contains carbon on both sides, then it produces a ketone like it did over here. And if one of the carbons contains one carbon on one side and one hydrogen on the other side, then it produces an aldehyde, which results in production of a carboxylic acid. So G should be C double bond O, OH, and CH3. That should be G. That should be G. Okay. So let's eliminate G out of it. So let's eliminate G out of it. So we have this structure remaining. And this structure, if you look at it closely, it looks like this, right? And it must be an alcohol. So it must be this, right? This should be our J. This should be our J, right? So because this is J, we know that Eve had a Br over here and J just has an OH over here. What must have happened? This must be a nucleophilic substitution reaction. And how do we produce an alcohol from a halogenoalkane? We add aqueous sodium hydroxide. We add aqueous sodium hydroxide. This is something we have to add over here. Okay, this is the thing we have to add over here. Next question, we want to go from C to G because C to G and C to ketone we just discussed. This must be an oxidation reaction, right? This must be an oxidation reaction. And alkenes, how can we oxidize them? How can they be oxidized to ketone and aldehydes? By reacting them with hot concentrated acidified KMnO4 aqueous. All right. So this is the reagent you have to use. You just have to use K-4. It must be hot, concentrated, and acidified. That is something you have to keep in mind. On to the next question. J plus G gives H. Okay, so J and G, they are reacting to produce H, and H is an ester, right? For ester, what do you require? You require H2SO4, a dehydrating agent, right? So you want to say concentrated H2SO4 as catalyst, right? So to make an ester from alcohol and carboxylic acid, we use ester because it is a good dehydrating agent. All right. On to the next question, beta. Figure 3.1 describes a sequence of reactions that can be used to produce a food additive compound Y from CH3CH2Cl. CH3CH2Cl gives CH3CH2Cn. Dilute acid gives CH3CH2COOH gives Y. All right. So this is the situation that is going on over here. So CH3CH2Cl is reacting to produce CH3CH2Cn. So we are producing from a halogenoalkane to a nitrile compound, right? So this is produced by one thing and one thing only. We produce it by ethanolic KCN, right? It is mentioned in the notes as well. All right. I think I can just show you from some summarized version, but it is also mentioned in other places as well. Uh, Organic synthesis, right? And if we want to produce a nitrile, which is ACN, what do? Nucleophilic substitution of halogenoalkanes with ethanolic KCN. We do ethanolic KCN, okay? So ethanolic KCN is the answer over here. Ethanolic KCN. KCN is potassium cyanide, right? KCN is potassium cyanide. This is what we have to add to step 1 to produce CH3, CH2, CN. Okay. Next, give the systemic name of X. What would be the name of X? Because it contains 1, 2, 3 carbons, it's going to be called propane nitrile, right? Because it contains nitrile, therefore it must have nitrile in its name, all right? And because it contains 3 carbons, its name should be propane nitrile. Propane nitrile. Next question. Identify the type of reaction that occurs when dilute acid is added to X in step 2. So what would be the type of reaction that would happen when dilute acid is added to X? So when a dilute acid is added to a cyanide or a nitrile, right? So whenever acids are added to nitriles, a type of elimination reaction takes place. Sorry, not the type of elimination reaction, type of hydrolysis reaction takes place. It's a type of hydrolysis reaction takes place. And as we can see, the type of hydrolysis reaction that takes place because the addition of dilute acid produces a carboxylic acid. This is also present in the notes where in two places. Where one place is when we were studying carboxylic acid, we learned how to prepare carboxylic acid from a nitrile compound by adding acid, right? Or by adding a base and then acidification of the base. Or we also studied it in reactions of nitriles as well. Okay, so in both places, the reaction is called hydrolysis reaction. The reaction is called hydrolysis reaction, right? The next question in step 3, why and a gas are produced? In step 3, when you react the carboxylic acid with the metal calcium, right? A gas is produced and Y is produced. Okay, so of course we know what Y would be and we know the gas that would be produced. But you should know that whenever you react an acid with a metal, two things are produced. When an acid reacts with a metal, salt and hydrogen gas is always produced. All right. So over here as well, when you react CH3, CH2, COOH, When it reacts with calcium, it's going to produce one compound and hydrogen gas. Now the compound that it would produce would be the alkanoatine, this much, right? This is a -1 charge, and calcium has a +2 charge. So this one charge will go over here, and this 2 charge will go over here. So the formula would become CH3, CH2, COO whole twice, Ca. This should be the compound Y that should form, and it should be called calcium. And because it's a 3-carbon carboxylic acid, propanoate. All right, and then along with that, the kind of gas that is being produced is H2. So we are going to say plus hydrogen gas, plus hydrogen gas. But you should know how to write these formulas by now. Okay. So all carboxylic acids have a -1 charge on them when they ionize. Okay. So whenever metal joins with them, we just switch the valences around. Next, CH3, CH2, COOH can also be formed from propane phenol and potassium dichromate. State the conditions required. So how can we produce carboxylic acid from propanol and potassium dichromate? So we've explained it. It is to heat the mixture, right? Heat the mixture under reflux, and when we want to use potassium dichromate, we have to acidify it. So we are going to say add few drops of concentrated acid, add few drops of concentrated acid, and heat under reflux, and heat under reflux. Next question. Complete table 3.1 to show the number of sigma bonds, pi bonds present in a molecule of X. So molecule of X, where is X? So this is X, right? This is X. So let's just draw it completely open, right? Because otherwise it would be very difficult to identify. Carbon, 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 and then nitrogen. And nitrogen has 3 bonds. So I'm going to draw the first bond with blue, and then the second bond and the third bond we can draw them as red. Okay, there is a reason for that, and I will explain. Okay, so now all the other guys had hydrogens attached to them. This carbon has no hydrogens attached to it. Its 4 bonds are complete. So we have this hydrogen, okay, and then we have this hydrogen right here, this hydrogen right here, and then we also have a hydrogen over here. All the other places also contain hydrogens. Right? All the bonds that are drawn with sigma, with blue are sigma. And why are they all sigma? Because every first bond between two atoms, is always sigma. Okay. So both carbons made 4 bonds each with sigma, and then this carbon double triple bond nitrogen as well. The first bond that would have been formed out of the 3 is sigma, and then we have 2 pi. 2 pi. Okay, so now let's number it out. How many sigma bonds do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 sigma bonds, it seems. Okay, and how many pi bonds do we have? 2 pi bonds. Next question. 1,3-dichloropropane to all can be made by reacting M. All right, so we can prepare 1,3 whatever dichloropropane to all. Okay, this compound by reacting M. So this is M. Okay, give the systemic name of M. So what would be the systemic name of M? Better, the systemic name of M could be, look. So the names. This is a carbon. This is a carbon, and this is a carbon. So there are only 3 carbons. This is the first carbon, second carbon, and third carbon. If you wanted, you could name it the other way: first carbon, second carbon, third carbon. It does not make a difference. All right. So first carbon, second carbon, and third carbon. All right. So the name would be 1,3 dichloro. Why 1,3 dichloro? Because Cl is joined to carbons on the first and third position. All right. 1,3 dichloro, and then this is a carbonyl compound with a ketone on it, right? So it's going to be called propane 2,1. All right, because the carbon double bond oxygen is on the second carbon, so we are going to call it 1,3 dichloropropane 2,1. On to the next question. Name the functional group present in M that changes during this reaction. So which functional group in M changes during the reaction? So the functional group that is present in M that changes during the reaction is the carbonyl carbon, right? The carbonyl carbon. Because look, chlorines do not change. Only the functional group that changed was the carbonyl carbon joined to hydroxyl group. Uh, State a suitable reagent for this reaction. What would be a suitable reagent for this reaction? Meaning, what do we use to convert a ketone into an alcohol? And because ketones are oxidized form of alcohol, so to come back to alcohol, we reduce them, and for that we use the reducing agent LiAlH4, or we could also use sodium NaBH4. Right, sodium boron hydride is also a thing we could use. Okay, on to the next question. Separate samples of 1,3-dichloropropane-2-ol and 3-chloropropane-1,2-diol are heated with excess acidified chromate ions until there is no further reaction. In each reaction, a different organic product Q or R is made. 1,3-dichloropropane-2-ol, it reacts with Q, or it forms Q, which is 3-chloropropane 1,2-diol, and it produces R. Okay. Q and R are tested separately with 2,4-D dinitrophenyl hydrazine solution, 2,4-DNPH, and sodium carbonate solution, Na2CO3. Complete the table to give any relevant observations. If no reaction occurs, write no visible change. If no reaction occurs, write no visible change. Okay. So 2,4-DNPH observation with Q. All right. So because this guy and this guy are both reacted with chromate ions, this is an oxidizing agent. This is an oxidizing agent, right? So it should produce OH, like this. All right. So now after oxidation, the OH vanishes, and what happens is this becomes a ketone. This becomes a ketone, right? After oxidation, this only becomes a ketone like this. Okay, so this is what happens. Now similar situation would be observed over here, but just a little bit different, and the difference would be that this, because this is what we call a secondary alcohol, it's connected to two carbons, we want to produce a ketone. This is a primary alcohol, it's only connected to one carbon. This would be upgraded this would be upgraded to a carboxylic acid, all right? Because primary alcohols, they oxidize to produce carboxylic acids like that, okay? So this will become a carboxylic acid over here, this one, right? So this will be upgraded to a carboxylic acid. Now let's see what would happen. 2,4-DNPH test, because they both contain the carbonyl carbon, the ketonic functional group, they should both give orange precipitate orange precipitate form, right? So they should give orange precipitate form, both of them. Now the next, sodium carbonate, because this compound contains no acidic group, it will give no reaction, no visible change as they have instructed us to do, right? No visible change, okay? But for the R, for the carboxylic acid, because it contains the carboxylic acid group, carboxylic acid group, they react with sodium carbonate or strong metal carbonates and produce salt, water, and carbon dioxide. So over here, the observation is whenever a carbonate reacts, gas is produced, right? So we say effervescence of a colorless gas, right? Effervescence of a colorless gas, all right? Okay, so now on to the next question. Citric acid can be made from M in four-step reaction. So let's take M and start making citric acid. We don't really know citric acid, what it looks like or what it is, but we can see that citric acid looks like this, okay? What happens is in the first step, what do we do is convert this ketone into hydroxynitrile. How do we convert it into hydroxynitrile? How do we convert anything into hydroxynitrile? It is very simple. We will see because we have to put the reagents over here in the type of reactions. So let's start talking about it. So how to con how to convert a ketone or an aldehyde into a hydroxynitrile? All you have to do is react HCN in the presence of ACN as catalyst, right? So react HCN in presence of KCN as catalyst. HCN in presence of KCN as catalyst. Okay, so this is the reagent and condition. Now the type of reaction, what kind of reaction is this? What kind of reaction would this be called? This would be called a nucleophilic substitution. Sorry, it won't be called a nucleophilic substitution reaction. Why? Because the compound is being added onto the molecule, right? It is added onto the molecule. The whole of HCN is added onto the molecule. No side products are formed. So this is called nucleophilic addition reaction, right? This kind of reaction should be called a nucleophilic addition reaction, okay? And the next is dilute sulfuric acid. On the second one, when you add dilute sulfuric acid, the nitrile always converts into the carboxylic acid, and the type of reaction is called hydrolysis. All right, whenever you add a sulfuric acid or any strong acid on a nitrile, it always converts into a carboxylic acid by hydrolysis. If you ever don't know how to write the equation for this beta, let's take an example and always follow this example, right? So for example, you have CH3CN. This is called ethane nitrile. If I add concentrated sulfuric acid, let's suppose, or I add concentrated hydrochloric acid, all you have to do is better write like this: H2SO4, yeah, HCl, whatever strong acid, and then you have to write H2O as well, okay? And then what you are going to do is you are going to write CH3, COOH plus NH4, and then if it was sulfuric acid, it would be ammonium sulfate. If it was hydrochloric acid, it would be NH4Cl, ammonium chloride, all right? So these are the compounds that are formed whenever a strong acid reacts with nitrile. There is always water because acid is always in water. So the kind of reaction is called hydrolysis because the H and OH breaks over here as well. I hope that makes sense. Better, do you guys understand? I hope so. If you had, if you didn't know this, just write it down. Okay. On to the next question. So in reaction three, what is happening? So in reaction three, we see that these guys also become nitriles, right? So how did we convert halogen to nitrile? Ethanolic potassium cyanide, right? Ethanolic KCN, right? Ethanolic KCN plus we also had to heat the mixture. We also have to heat the mixture, okay? This is what we call the nucleophilic substitution reaction. Nucleophilic substitution reaction. We had just seen it written in the previous slide. Substitution reaction, right? It is written in the previous slide right here. We studied if you want to make nitrile, the reaction is a nucleophilic substitution reaction of halogen alkanes, and you use KCN and heat. Okay, so this is exactly what we have written over here. Next question, reagent and condition. When you add to number 4 dilute sulfuric acid, so these guys also become carboxylic acids. This is once again the type of reaction is called hydrolysis reaction. The type of reaction is called hydrolysis reaction. All right. I hope that makes sense. Okay, beta. On to the next question. Question number 5. The diagram shows a reaction sequence starting from ethanol. All right. Ethanol is going to be reacting with HCN or NaCN in reaction 1. So right here you can see it is HCN and NaCN. We usually generically use KCN, but it would do the same thing, I suppose, and it would produce a hydroxy nitrile compound, right? Hydroxynitrile. And then you are putting H2SO4, and you're seeing that the nitrile is going to convert it to carboxylic group. The hydroxy remains in its place. And then in reaction 3, you are seeing that a double bond is forming. Now, how would a double bond form? The answer is very simple. Look, the COOH group is still there. The OH has vanished all of a sudden, right? All of a sudden, the OH group has disappeared. And along with the OH group disappearing, one hydrogen from this carbon has disappeared. As you can see, this carbon previously had CH3, 3 hydrogens. Now it has 1 hydrogen. So this has just removed water, right? So plus H2O has happened over here as well. Okay. And then there is also another way of reacting Q, and another way of reacting reaction 4 or Q is to convert it into a ketone. Now, how do we convert it into a ketone? It is very simple. Look at this alcohol. This is a secondary alcohol. This is a secondary alcohol. How could it have gone into becoming a ketone? Secondary alcohols, when they undergo oxidation, they become ketones. Okay? So this is oxidation. This is elimination. Right? This kind of reaction is elimination. This kind of reaction, we say nucleophilic addition reaction, as we had discussed, nucleophilic addition reaction, right? And then H2SO4, this kind of reaction was the hydrolysis reaction, breakdown of water. Draw the displayed formula of P. The displayed formula of P would mean that we have to draw every single bond, right? So let's draw every single bond. The carbon's in the center. The OH is on the top, right? The OH is on the top like this. And then there is a CH3 over here. The carbon, hydrogen, hydrogen, and hydrogen. All right. And then we have a nitrile at the bottom, the carbon, double bond, triple bond, nitrile. And then we also have what is over here? Hydrogen is over here. All right. So this is going to be our compound. It's called 2-hydroxy propane nitrile, right? It's called 2-hydroxy 2-hydroxy propane nitride. 2-hydroxypropane nitride. On to the next question. Name the type of chemical reaction that occurs in reaction 3. What kind of chemical reaction is occurring in reaction 3? So we've mentioned the name right here. The reaction is elimination reaction. What kind of reaction is happening? Elimination reaction is taking place. All right, beta. So I hope that makes sense. Elimination reaction is taking place. On to the next question. Write an equation to represent reaction 4. Use O to represent the oxidizing agent. Use O to represent the oxidizing agent. Okay, so we want to show what is happening in reaction 4. Well, they've like literally mentioned you can write O as oxidizing agent. Let's write CH3 C O H C double O H. This is not complete. I've missed an H in the above equation, right? This is H right here, okay? And then we are going to react it with oxygen. All right, but I have written it like this. If you want, you can write it in another way as well. Like for example, you can write like this: CH and COOH, all these things in a single line, and then you can write O on top, OH on top as well. All right, because they've given us a space to write OH on top, we can write OH on top like this as well, no problem. Okay, and then what happens is that you get CH3, C double bond O and C double OH. Okay, so if we notice how many hydrogens have left, two hydrogens have left, and the oxygen has joined, and this OH has also left. So we are going to produce plus H2O. So along with H2O, this is what is produced. On to the next one. State the reagent and conditions for reaction 4. So what are the reagents and conditions? We know it is acidified, acidified KMNO4. Yeah, acidified KMNO4. We need the oxidizing agent, right? And it could be in aqueous condition. Acidified aqueous KMNO4. Okay. So this is the reagent and condition. On to the next question. R can be used to make a polymer W in 2 steps. So R can be used to make polymer W in 2 steps. So the first step is R becoming addition polymerization, and then it is reacting with NaOH to form W. Okay, so first of all, what is R? Okay, so this is R. Okay, so let's take R downstairs for interrogation. So R is a carbon double bond carbon, and if you remember R is just a carbon double bond carbon. This guy has 2 hydrogens. This guy has a C double OH. Okay, and then it has undergone addition polymerization. Okay, so first let's make its addition polymerization. All right. So what would happen is very simple and basic. This whole thing would remain the same, just the double bond breaks, right? During addition polymerization, the double bond breaks. That is all that happens. So the double bond breaks, right? Only a single bond is left, beta, and then the double bond just makes extensions on both sides like this, right? This is the partial structure of uh, from R to the addition polymer, which is the intermediate polymer. Now this guy reacts with NaOH. Okay, so let's just copy it down. This guy reacts with NaOH. All right, and now the purpose of NaOH, or how could it even react with NaOH, is because of the presence of the carboxylic acid, right? So how many NaOH would it react with? However many this n is, because जितने ये n की value होगी, that many carboxylic acid would be in the polymer. So we will write n over here. Okay, and then we write the formula. Duplicate this. So the same compound should form, but instead of the H at the end, what should be at the end over here, right here? Na, right? It should be Na, and that H must have formed H2O, because acid and base. This is the acid, this is the base, and when acid base react, they form salt and water. So now this is also a salt. There is also a salt substance in the addition polymer and water. And how many water molecules? N number of water molecules. Well, they just asked us to draw the repeat unit of W. So you have to highlight the repeat unit of W. This is the repeat unit of W, right? This was a 3-mark question because it required all this. All right, so this is the repeat unit of W. Okay, so this is what the reaction looks like. It was this easy, beta. The whole paper was actually pretty easy. I'm sure that you guys might have found it a little tricky because you are still practicing. Okay, but once you start understanding that organic chemistry is just functional groups and their reactions, no matter how complex the molecule looks like, If you look at these reactions and these molecules look pretty complex for you guys. But just focus on the functional groups. What is happening to the functional group? The ketone has changed into a nitrile and a hydroxy. So this is a hydroxy nitrile. So just focus on functional groups one at a time and you guys will understand how to do them. All right. I hope you guys understand everything clearly.